Welcome to the Problemers Channel, Season 3, Episode 43, the episode which I titled The Kinematics of Wile, Coyote, and Roadrunner, because in this episode we will solve a classical pursuit problem where a runner moves along a straight line with a constant speed and a constant velocity, obviously, and a chaser is located somewhere off of that straight line, but in the parent plane. Before we deep dive into the underlying kinematics of that problem, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page in the channel's trailer section, find the episode titled The Problemers Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do, and in 2 words or less, who we are and what we do on this channel. We basically solve problems in mathematics, physics, and computer science forever and ever. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that resonates with you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current subscribers and the current supporters of our channel, and especially to the people whom I know personally from work. Thank you very much for your support, for your help and useful suggestions. And one small announcement for both the newcomers and the veterans of this channel alike, because recently I'm being asked on a regular basis, how do I use this channel in addition to the video information, which I explain how to use this channel correctly, and I already told you how to get to it. I've put together a written document called How To, and the link to that document, the free PDF file, is in the comment section to this episode. In the physics problem S3P10, we're given 2 points, the point R and the point C, that execute continuous motion in the given parent plane as follows. The point R is moving along a straight line with a constant velocity and a constant speed, which means the vector of the runner's velocity, R, points in one and the same direction, and the magnitude of that velocity remains constant over time. The point C is located not on that straight line, but somewhere else in the ambient plane, and the vector of that velocity of the point C, or the chaser, always points at the point R at any given time. However, we're told that the magnitude of the velocity of the chaser, Vc, is also a constant quantity. Under these conditions, we're asked to recover the following information. First, we need to construct the trajectory of the chaser, or the point C. This is known as a curve of pursuit. Number 2, we're asked to recover the condition and the coordinate of intercept, at which point and under which conditions the point C can actually intercept the point R. And the third and the final unit of information that we're asked to recover is to compute the time of intercept. If the following information is given: when the vectors of the velocities of the runner and the chaser were orthogonal with respect to each other, the distance between the points C and R is known and given to us as d0. Once the problem statement is understood, we will begin the discussion of our solution of this problem with the reasons why many students fail to solve this particular problem, and specifically why many students fail to convert the initially mysterious condition that when the velocities of the vectors of the chaser and the runner are orthogonal, the distance between the points is given, into actionable physics and actionable mathematics. As I mentioned earlier, if you can solve this problem on your own correctly, especially in the way in which we will solve it right now while you're in high school, you're doing exceptionally well. Good for you, congratulations. If you can solve this problem, especially the way we will solve it right now while you're in your first year in college, you're doing very well. If you're in your second year in college, you are pretty much expected to solve this problem. And third, if you cannot solve this problem while you're in the third year in college, then we have a problem. And it goes without saying that the graduate student is expected to solve this problem correctly on his or her own at that point in their physics career. Now, most of the problems, not actually most, all the clean academic textbooks problems are given to you during the course in physics or mathematics or any other course is precisely because these problems can be solved in a reasonable amount of time, and no one in their sane mind will give you a problem that cannot be solved without actually telling you about that fact up front. Now, the other side of this coin, that the problem that you're given is clean textbook academic problem that can be solved, is the following fact: that most people who fail to shed their high school skin do not know. The data, the amount of information that is given in the problem statement, is dialed in optimally, which means the amount of that information and the quality of that information is dialed in perfectly, so that if we take one unit of information away, then you will not be able to solve this problem at all, no matter how long and how hard you try. But if any extra, at least one unit of information is thrown into the mix again, then your certainty about in which set of parameters you should generate your answer to that problem goes to zero. In other words, should you solve the problem using this set of parameters or slightly different? That's a question you cannot answer. That introduces the confusion, and that is why, in theory, you cannot solve this problem in this specific way. And that goes back to the optimal dialed in number and the quality of parameters. With this particular set of input parameters, the problem can be solved in a specific way. So in some sense, the problem statement for you is already a hint. And many students who enter college, especially during their first year, they fail to shed their high school skin, and while wearing this high school skin on them, they do not know that the other side of this situation with the clean textbook academic exercises is the fact that they literally have to squeeze multiple units of information, or as much information as possible, literally from every word and from every letter of the problem statement. So this is the first fact why many students who take on this type of problem cannot solve it. They read the problem statement, they try this, they try that, hectically, perhaps haphazardly. Oh, this problem is too difficult, I cannot solve it. No one taught me how to solve it. That's number one. Number two, after you know that you have to literally fight academically, of course, for every character, for every word in the problem statement, and squeeze as much information, as many bits of information from that word and letter of the problem statement as you can, is the other side of it is knowing how to extract that information. And here, one of the fundamental reasons why people fail to solve this particular problem is because they overlook the critical unit of information that is given to us over here in this statement right here in the third question, even though, again, later on you will see, even without this information, you should be generate the information that I'm about to generate. But here, remember, one of the other main and important aspects of a hard scientist is to always be skeptical, always ask questions, always be in doubt. Here, the situation is the following. If you're always skeptical, as every hard scientist should be, you should be asking the following question: why the vectors of the velocities of the runner and the chaser must be or should be or can be orthogonal with respect to each other to begin with. Says who that it must be so? Well, apparently, the author of this problem statement thought about it, realized what's going on, and gave us this information as a hint. So our job, our mission, should we choose to accept it, is to unwind that little mystery and convert it into actionable physics and actionable mathematics. And this is precisely where students fail. And again, the reason why they fail, as I promised you a few seconds ago at the end of the previous segment, is because these students fail to shed their high school skin. They still think like high schoolers. And while you think as a high schooler, these grown-up problems will be out of reach for you, because no matter how much theoretical material, no how much theoretical textbooks you can read, you will never shed your high school skin if you are not able and if you are not in the mode of solving specific problems. So here, the key observation is the following. We ask ourselves the following question: why the vectors of the velocities of the runner and the chaser are perpendicular in the first place? Where did they come from? Why it must be so? Well, here is a line of reasoning which pretty much you will never generate while you're still wearing your high school skin. The key observation here is the following. At some point, our runner R was where? Well, here's the thing. Because the runner, we're told the runner, the point R, moves along a straight line, then that straight line is very naturally converted into the x-axis of the future coordinate system, in which we will construct the shape of the trajectory of the chaser point C. The question is, if we made that decision, and this is a good first step, the question is where on that straight line where there should be the origin of our coordinate system, and why? Well, here is the line of reasoning that answers that question, and we unlock the, again, answer to the question, what does it mean that these two vectors are orthogonal with respect to each other? First, we observe that at some point, the runner R, our x-axis can be partitioned roughly, let's say, into three sections: the negative infinity, the positive infinity, and somewhere in between, where the interesting things happen. So when the point R was at negative infinity, then the vector of the velocity of the chaser C was pointing where? Well, at this point, look at this. This is the line of reasoning that you're expected to generate. And again, many students will fail to solve this problem even in the kindergarten conditions when they're not bothered. But in my time, this was a typical specimen for a verbal, real-time, face-to-face interrogation examination in theoretical physics, where you'll be given 15, 20, 30 minutes to gather your thoughts. Then you step up to the plate, and then face-to-face in the real time, perhaps even using the board, you explain to the professor how you will solve this problem. The professor will ask you questions relevant to this problem, give an alternative reasoning. Can it be done the other way? What does that mean? Elaborate, and so on. So in that format, in the format of real-time verbal communication, students fail left and right all the time, precisely because they're still wearing their high school skin, and they cannot generate these arguments. But here is the thing. If the runner R was at negative infinity, then the vector of the velocity of the chaser, look at this, this is the vector of the velocity of the chaser, was parallel. It was parallel. The chaser was parallel to the x-axis, and it was pointing where? Well, it was pointing logically leftwards, this way, towards the negative infinity. And what is the angle between the velocity vector and the x-axis? Well, let's symbolize it as follows. The velocity of the vector of the velocity of the chaser, angle with the x-axis. If we are very pedantic and we want to measure this angle clockwise, is a traditional positive direction, counterclockwise is negative direction. let's say we measure it as a negative pi, for example. You can put plus pi, it doesn't really matter. This is one observation. Now, when the runner r goes into positive infinity, when the runner r is over here in this section with positive infinity, then what will happen to the vector of the velocity of the chaser? Well, in this case, the chaser, the velocity of the chaser as a vector will also be parallel. In this case, the vector of the velocity of the chaser will be parallel to the x-axis also, but it will be pointing where? Rightward. Exactly. It will point rightward. So let's say the angle between the velocity vector of the chaser, I will symbolize it like this with the cap, and the x-axis will be 0 radians. Let's say this one, and we'll measure it in radians. However, what is the next observation over here that you're expected to make while you convert this initially mysterious unit of information into actionable physics and mathematics? Well, the next observation that you're expected to make over here is that the motion of both points, the point R and the point C, is what? It is continuous. It is continuous. Now, if the motion is continuous, then we reason that we can construct a function f that takes the mutual juxtaposition of these 2 points, C and R, as an argument, and it pumps out what? It pumps out the angle, let's call it alpha. The angle alpha, which is formed by the vector of the velocity of the chaser and the x-axis. And what do we do now? Precisely because the motion is continuous, we recall the so-called IVT. This is where you bring in the knowledge, your knowledge of real analysis, the intermediate value theorem, which says what? If the function is continuous and our vector always points, our vector of the velocity of the chaser always points at the runner, then from its extreme value of plus minus pi to another extreme 0, this vector changes its position. Which way? Continuously. Somehow the point, of course, will be moving, but this vector will be changing its direction as the point as C is moving, and eventually it will point this way. And what does that mean? That means that at some point the angle, let's say our angle alpha, will be between minus pi and 0. So that means that at some point that angle will be pi over 2, let's say negative pi over 2 if we want to keep our signs, and according to the IVT, the intermediate value theorem, for that value of the function there exists the corresponding argument. That means that for that particular angle between the velocity vector of the chaser and the x-axis, there exists a mutual juxtaposition of the points C and R such that the angle between these two vectors is 90 plus minus 90 degrees, depending on how you keep track of your angles in which direction, but fundamentally these two vectors will be orthogonal, and this is precisely the time, and this is precisely the configuration, the mutual juxtaposition of the points C and R, at which the distance between them is caught to be d0. And this is precisely the moment in time and the moment in the mutual juxtaposition of these 2 points that locks in the origin, the position of the origin on our coordinate axis x. And through that point, this will be the point O, through that point, they will run another coordinate axis, to which we refer as y, perpendicularly or orthogonally to the x-axis. So our y-axis will run this way. This will be the y-axis. This is the right angle. And at that point, what do we have? We have our point O is exactly the same as the point R. Here is the point R also. Here somewhere on that coordinate axis y, there will be the point C. This distance will be d0. And let's take even the, I don't know, yellow maybe color. See, the vector of the velocity of the chaser will be pointing this way at the point R, and the vector of the, I can grab maybe this one. Well, let's take red color. And the vector of the velocity of the runner will point this way. You see, this is the situation, and the angle between them is fundamentally pi over 2 radians or 90 degrees, plus minus, depending on how you keep track. But this is essentially and fundamentally the mutual juxtaposition of the points which lock in the position of the origin of our coordinate system, in which we will construct the shape of our trajectory. Not only that, but remember that because this is classical mechanics, this is not quantum mechanics, this is classical mechanics, every classical particle possesses their radius vector, let's say function, which is what? At least twice differentiable. The first time derivative of the radius vector is the velocity, and the second time derivative is the acceleration. And we also know from the fundamental kinematics that the velocity vector is always what? Is always tangent to the underlying trajectory of the moving particle. So from this seemingly innocent and initially mysterious unit of information, in addition to all of this information that you're expected to generate, let's say in the best case, in the verbal real-time face-to-face examination on theoretical physics, we can also extract what unit of information? We can extract the following unit of information. At the point C, when the vectors of the velocities of the runner and the chaser, at this point, the coordinate axis y plays the role of what? It plays the role of the tangent to the trajectory of the point C. So this trajectory, we can already theoretically roughly sketch out the graph of that function. We can roughly sketch out the shape of the trajectory. Will look as follows, and that fact over here actually will be converted into actionable mathematics a few segments later, but chalk it up into your, store it in your memory, this information over here. What does that mean over here actually, this fact? I do not want to put too much technical information into this first segment, but this information alone already can be converted into actionable mathematics. And what is the actionable mathematics over here? Well, if we take the first derivative, dx over dy, it will be what? Precisely 0 at that point. Because if you rotate this axis this way and let's say look at this way, you have a graph. Here there's a tangent, and what is the condition of the tangent? It is parallel, so the angle is 0 degrees, so the derivative at this point is what? Precisely 0. And we will use this fact a few segments later, but look at how much actionable physics and mathematics we can generate if we shed our high school skin, step into our first or second year in college, and fight for every unit of information that is given to us in the problem statement. And that is how much information we can extract merely from the fact that someone very cleverly gave us a hint in the problem statement that it does so happen that the vectors of the velocities of the runner and the chaser are orthogonal at some point, and we're told what the distance is. So this distance right here is d0. This is the mutual juxtaposition. We know roughly the shape of the trajectory, and we know that the first derivative of dx over dy over here is what? Is precisely 0. And what do we do now? How do we convert all these observations into even more actionable mathematics and physics, and how do we unwind a solution of this problem? Once we break down the solution of this problem into very straightforward, almost middle school steps, one by one after another, and show the solution to the students who fail to solve this problem, the students invariably say, well, gee, that was very simple. How come I did not solve this problem that way, and how come I did not generate this line of reasoning? Well, that's precisely the point. On this channel, this is precisely what we do. We show you how to do this, and hopefully you will learn how to do these things on your own, and you will be able to solve similar and even more complicated problems. And also, hopefully, you will share your wisdom with us. But here, again, in a matter of as simple as possible, but not simpler, we already understand how these objects that we put on the right side of the screen came into existence. The x-axis was chosen because it is a natural choice for the first coordinate system in our case, because the runner r runs along a straight line. We're given that much. You already saw the line of reasoning that fixes the origin of this coordinate system and explains how the vertical axis, the y-axis of this coordinate system, comes into existence. That much you understand. You understand why the graph, the partial graph of the trajectory of the chaser C, shown in yellow, looks precisely that way. Why the vertical y-axis of our coordinate system plays the role of a tangent to that graph. We know the basics, the basic kinematics, velocity, and so on. We call this point d0, and this distance from here to here is d0. I do not want to pollute the our diagram too much. You understand what is going on. You can call it c0 if you want to, but it doesn't really matter. So now, once you understand how all these objects came into existence, and hopefully and ideally you should be able to generate all that information on your own correctly and put this into motion that way, we now make the following assumption. Let's say that starting from this point over here, and don't forget, remember that at the point O, what did we say? At the point O, we have the point R initially, but this is also the moment of time where we click, launch our timer. So from this point, the time is 0. This will be important for our integration, and we will take all sorts of integrals, but the boundaries for these integrals will come out naturally from these observations, from this information that we generated. So if you keep this picture in mind, you'll have absolutely no problem in generating correct boundaries of integration, and the number of such boundaries we will generate in the upcoming segments, left and right, they will start growing like mushrooms after the rain. So if we launched our timer, ka-ching, when the point R was at the origin, which we explained how to construct, then in this unit of time, where did the point R get? Well, the point R covered the distance OR. And what is this distance? Well, again, this is going back to my promise to be as simple as possible, but not simpler. This is basically middle school observation. This is not even college physics. So this will be the velocity of the runner, VR, times the unit of time t, because the motion is uniform and in a straight line. Wonderful. So from here, what does it follow? Again, this is a baby step. The time t is equal distance OR divided by the magnitude of the velocity of the runner, VR. Now, the thing is, here is another observation that we make. Starting from this point, at the moment of time t0, when the point O was at the point R, or in some sense, the point R is the origin at that point of time, our point C was right here at this point, and then it started moving again continuously over its trajectory. But the thing is, even though the trajectory of the point C of the chaser is a fancy looking curve, and we will develop the analytic expression for that curve in a few minutes, the fact that the point C moves over that trajectory at the same rate does not change the fact that this is so. And that means that if we designate this arc right here, let me use the yellow color, this arc right here, let me designate it in this perhaps fancy way, but you understand. This is the arc length from the point D0 to the point C. In time t, the point C went from here to here, while its velocity vector points to the point R at every time. It pointed to the point R this time, then it moved here, this way, here, this way, here, this way, and so on. You understand that as progression happens, you can even use the divide and conquer problem solving approach take snapshots of this motion at the regular small intervals delta t and see construct the bunch of vectors, and you will see an interesting picture. Actually, it is a good exercise. But we will designate this as the arc S. This is the arc length. So over that trajectory, the point C traced this portion right here, S. So that distance, even though it is curvilinear, it was still covered. That distance was covered in which way? It is given by the product of the velocity, of the magnitude of the velocity of the chaser, which is a constant quantity, times the same value, the same time t. See, the time t here and time t here, they are exactly the same. So from here, it follows that during the same time t, we have the following relation: S divided by vc, velocity of the chaser. Again, it should be understood that S over here is the arc. Let me put it this way. S, do it in yellow again so it's easier for you to see. S is the arc, let's say D0C. This is the arc D0C, this portion right here, curvilinear portion. And now we have this relation. So here from these two relations, because this is one and the same time, the time t is one and the same. Let me hopefully catch it in this one. So this time t and this time t is the same. And from the fact that these times are the same, we have the following relation already. T is equal to S divided by VC, and this is the same as OR divided by VR. So this ratio we have. And now what do we do? Well, now actually, again, keeping it as simple as possible, what do? We do what we do in middle school. We project the velocity vector of the chaser C on the coordinate axis. Now, it is important to understand that the point C over here is what? It has the coordinates X and Y in the chosen coordinate system, which you understand how we construct it. And why do we introduce this symbolic notation? Well, precisely the property of these coordinates X, Y is such that the numbers x, y belong to the trajectory, let's say graph, to the graph G. This is precisely what these numbers are. So if we manage to cook up a relation between x and y, boom, we have our shape of the trajectory and problem solved. So first we project our vector VC on the x-axis and on the y-axis. So here at this point, which way will it work? Well, first of all, we take our point C and we project it orthogonally into the point P onto the x-axis, and we actually do the same over here, but here we will not need any letters, so I will not use it technically. This will be what? This will be the y-coordinate. This information right here, this distance right here, is the y-coordinate of the point C. And what is this? This is the x-coordinate of the point C. And again, you understand that the vectors will run, the projections of these vectors will run this way and they will run that way. This is the angle. Remember that the vector of the velocity of the chaser always points at the point R, no matter where it is along the straight line. So in that respect, if we connect the point C with the point R with a straight line, we always can do it prior to the intercept event. If and when the point C intercepts the point R, then these two distinct points in the Euclidean plane define a unique straight line. This straight line is right here, and it forms the angle alpha with the underlying x-axis. So what can we say about the, let's do it here, the velocity of the chaser C when it is projected onto the x-coordinate? What is it? Well, this is the first time derivative of the coordinate x, the x component, and it will be what? It will be the magnitude of the velocity of the chaser, which is a constant quantity, times the cosine of the angle alpha. The angle alpha, we understand, it will come again into use. It will enter the stage at the end of this episode when we will be computing the intercept time. But right now we notice that it is a somewhat perhaps complicated but interesting function of time. This angle changes with time. Once you construct this series of vectors, you will see that this is the case. But again, there is nothing, we don't really have to right now. Our objective is not to recover the shape of this angle alpha as a function of time. This is a separate business, and it's perhaps not so straightforward, complicated one. But here we go back to middle school. In middle school terms, what is this cosine? In middle school terms, this cosine will be, look at this, it will be the distance PR. It will be the distance PR divided by what? PR divided by CR, divided by the distance CR. That much is clear, right? This is nothing complicated. This is middle school definition of the trigonometric function of cosine. And what can we say about the distance PR? This distance right here. It is distance OR minus OP. So this is OR minus OP divided by CR. Now let's spell out what is the distance OR. We already know what it is. It is velocity of the runner times time t minus what is OP? This is x divided by CR. So far so good, wonderful. So let's recall, let's mark it that this is dx over dt. Again, make a good note of these relations because we will come back to these relations towards the end of the episode after we uncover the shape, the analytic shape of the trajectory of the Wile Coyote who is chasing the road runner. And once we do it for both cases when the velocities are equal by magnitude or not equal by magnitude, we'll come back to this, number them, mark them, take a mental note, but we will come back to this. Wonderful. So now let's write down the expression for the projection of the velocity vector of the chaser onto the y-axis. This will be what? By definition, this will be the first derivative dy over dt. Now we have to be careful over here. Once we project the velocity vector of the chaser onto the y-axis, it will go this way. What can you say about the sign? Well, the sign will be negative in this case because this velocity points this way, but the vertical y-axis points this way. So far so good. The cosine of pi is -1, so this is our -1. So here we carefully write. Let me even perhaps use the red chalk over here to make sure that we do not lose minus, just to make sure that we have it, minus the magnitude of the velocity of the chaser, which is a constant quantity, times sine of alpha, sine of this angle. And what does that mean? Let's write it over here. Minus velocity of the chaser times, how do we express the sine of this angle? Well, this will be the distance CP. This is the distance CP divided by the distance CR, the distance CR. And what is the distance CP? Well, this is the y coordinate of the point C. So this will be the magnitude of the velocity of the chaser with a minus sign, velocity times y divided by CR. You see? So now this is dy over dt. So now we take this equation, and we take this equation, and if we divide this equation by this equation, what will happen? Let's write it down over here. Dx divided by dy is equal to dt and dt cancel out, CR and CR cancel out, and what will we have? The velocity of the chaser here and here will cancel out, so we'll have the minus sign will survive. Here we have VR times t minus x divided by y. Remember, CR and CR cancel out. We take this minus sign, bring it into the numerator, and we have x minus v, the velocity of the runner, times t divided by y. But the time t Remember, when we need to construct the relationship between the coordinates x and y, and thus lock in the shape of the trajectory of the point C, which is our first objective, we need to do what? We need to exclude time. How do we exclude time? And splice the fodder, the material for the trajectory. Well, this is our guy right here. Look at this, S. So if instead of t, we put S over minus, instead of t, we put the arc length, S, times. Here we have the velocity of the runner, v, divided by the velocity of the chaser, and divide the whole thing by y. But this, look at this, what is this? This is a constant quantity. And what is this? This is another constant quantity. Constant quantity divided by constant quantity is a constant quantity. So instead of writing all this information over and over again, we will designate it with rho as a ratio, and this is a constant, right? This is still a constant. And that means that, let me erase, you understand how this information came into existence. Where do I have some room? Well, let me erase some room over here a little bit. You understand how this information was generated. Again, this is as simple as possible. This is nothing beyond middle school curriculum, but now we have the following. Don't forget dx over dy. So we have dx over dy is equal to x minus rho times s divided by y. This is our, look at this, this is our relation that you saw at the opening of this segment, and this is how we convert the answer to the original question, why or why the vectors of the velocities of the chaser and the runner must be perpendicular or orthogonal with respect to each other. Now that we know why, we convert this information into this here equation. And as a hint and as a spoiler alert, this is all we need in order to solve the first part of this problem. This equation over here unlocks an analytic shape of the trajectory of the chaser C. When I was writing on Quora, I saw my fair share of questions from the younger students that went like this. I want to do theoretical physics, but I'm not that good at mathematics. What do I do? The answer here is you need to get good with mathematics pronto, because I do not really see how anyone can get a degree, a basic degree in theoretical physics without being able to hold one's own in mathematics, because this is a very typical scenario that will be repeated and that you will see on and on again and again all the time in all the problems. Initially, a fair amount of solid physics first, then physics leaves the stage completely. On comes the mathematics, and you need to plow your way through nothing but mathematics. If you fail here, then you're not really going anywhere, and here is an experiment for you. You've been told already, even though I deduced this equation over here in front of your eyes in a public setting, no secrets, in as simple fashion as possible, you're told that this equation is all you need in order to uncover the analytic shape of the trajectory of the chaser C. How do you do it? Well, don't watch my presentation, put this video on pause, walk away, and try to do it on your own. See how far you can get. And then come back and compare your reasoning to mine. But here, we do the following maneuvering. Let's do this. Multiply both sides of this equation, of this equality, through by y. So y goes over here. And then swap this y times dx and rho times s with respect to the equal sign. So we will obtain the following. Once we do that, we obtain the following relation over here. X minus y times dx over dy is equal to rho times s. That maneuver should be understood. Y goes over here. Then we swap the differential and this, and we put it on this side. So technically what you see over here is an ordinary differential equation of order 1 with that is with separable variables, and the idea is to separate these variables into actionable material that we can eventually integrate and extract a certain, hopefully analytic relationship between x and y. Most of the time that's not possible. Sometimes it is possible. It is actually a miracle that it is possible. In this case, we're witnessing this miracle, and in some sense, remember, going back to my earlier remark at the beginning of this episode, that all these clean textbook, academic, pristine problems, you were given them for the reason that they can be solved. So here we will see actually there is something interesting going on over here. We will see what does it mean to separate the variables in such an equation. So here we have it, a middle school transformation. But now what? Well, now what we do is we differentiate both sides of this equality with respect to what? What would you do? You would differentiate this blessed thing with respect to what? With respect to y. This is one winning maneuver. So we differentiate both sides of this as follows. Dx over dy minus the first derivative with respect to y over a function that is a product. How we differentiate the product? Well, minus dy over dy times dx over dy. This is what? This is 1. So in some sense, we can omit this. This will be 1. So dx over dy minus dx over dy minus y times d2x over dy squared equal to another, the derivative, first derivative of a product. But this is what? This is a constant. I move it out, so it will be rho times ds over dy. Cancel. We have minus over here, don't forget, minus y times d2x over dy squared equals rho times ds over dy. What would your next maneuver be? What would you do over here? Well, look at this. This is the basic fact in differential geometry technically, but in various courses, in various countries, in various colleges, you can see this information all over the place. For example, in your course on real analysis, where you are given the example of the application of differential calculus to geometry, to physics, to chemistry, to whatever else the case may be. So in some sense, for this elementary, remember, this is our elementary. ds is a small elementary portion of the curve. The equivalent of the Pythagorean theorem holds. ds squared equals dx squared plus dy squared. You see? That information you know. And that means that ds will be written as plus minus square root of dx squared plus dy squared, with plus or minus taken depending on how we agree to measure the direction along a curve. In one direction it's a positive quantity, in the opposite direction it will be negative, so we have to take this sign carefully. But the thing is this, we now do what with this material? We need the first derivative of the arc length with respect to the variable y. So we do the same thing over here, and once we do that, look at this. We do it like this. ds divided by dy is equal to, what sign would you put in front over here, and why? The sign that you put over here, again, let me put this in red. It will be minus. The correct sign to take is minus. And here it will be square root of what? Once we move dy from the numerator into the denominator of the square root, we will have to square it. So dy squared over dy squared will be what? 1. 1 plus, and then what do we have? The ratio of squares. dx over dy squared. Now, why do we take the minus sign over here? Remember, a few seconds ago, you saw the graph over here. We take the minus sign over here because when the y-coordinate grows, what happens to the arc length? Arc length diminishes. Remember, it's coming back. When the y-coordinate grows or goes this way, what happens to the arc length? Arc length diminishes. At every point it becomes smaller and smaller and smaller, and the quantity is diminishing. Its first derivative is what? Is negative. Exactly. So let me move this expression over here one more time so you can see it clearly. The first derivative of ds over y is equal to minus square root of 1 plus dx over dy squared, and we take the square root of that with a minus sign. Now we put this animal into, where is my last equation? Right here. Into, let me erase this, you don't have to do this anymore. We put this over here, you see, into this guy. And what happens over here? Look, minus sign and minus sign. What does that mean? It means that these minus signs cancel each other out, and we have the following relation: y times d2x over dx dy, dy squared is equal to rho times square root of 1 dx over dy squared, like so. Agreed? So far so good. So now the idea is to separate the variables in such a way that we can eventually integrate something over certain boundaries, and the way we do it is as follows. We multiply this relation through by one copy of dy. Multiply by one copy of dy. You see, this is purely mathematics at this point. Going back to my remark before, there is virtually no physics, very little physics over here. Everything that follows is mathematics, even though technically, think about this. Right now, you're sitting or passing the verbal face-to-face real-time examination in theoretical mechanics. So there you go. You have the ability to judge now how much mathematics you need to know and what type of mathematical prowess you need to possess in order to pass such an exam. So here we do the following. Multiply this equation through by one copy of dy. So, and let's do this right away also. We move the square root on the left-hand side, but the y we move to the right-hand side. So what do we have? We have d2x over dy squared times dy divided by square root of 1 plus dx over dy squared. And on the right hand side over here, what do we have? We have rho times dy over y. That maneuver should be understood. Y from the numerator of the left hand side of the equal sign goes into the denominator of the right hand side of the equal sign. It goes over here. And the square root from the numerator of the right hand side goes into the denominator of the left hand side of the equal sign. This is, again, nothing complicated. Middle school algebra here, and this is what we have. Now, you already recognize the integral over here. This is a baby integral. We already see what's going on. But what is going on over here? Again, initially this looks scary, but eventually, once you go through these motions, once it becomes business as usual, and you will snort this type of expressions with your left nostril in one go. So here, let's do this. Let's spell out the definition of the second derivative. The second derivative, d2x over dy squared times dy is equal to what? It's d over dy of dx over dy times dy. What do you see? What magical cancellation do you see over here? The first differentials dy cancel out, and we have the first differential of this quantity, dx over dy. You see, this is what we have. So from here, we move into here. Look at this. d of dx over dy divided by square root of 1 plus dx over dy squared is equal to rho dy over y. And again, initially some students get confused by this. You should not really get confused by this. This is basic material, but as a symbolic sugar, we introduce the following substitution over here. Look at this. dx over dy temporarily, just mark it as z. Mark it as z. Then under this designation, what will you have over here? Well, you will have the following. dz over square root of 1 plus z squared equals rho times dy over y. You see, it goes like this. This is the expression that where we separated the variables and we prepared the material for integration. And if you can handle this, if you can swing it, you can work with this guy. But this is what's coming up next. Those of our viewers who are comfortable working with the original form of our differential equation with separated variables can work with this copy. It doesn't really matter. Just to make sure that everyone is comfortable, I will work with this one. But in general, again, it doesn't matter. Once you see this maneuver and execute this maneuver once yourself, you will be working with it, with this material, even the original form. You will be manipulating this left and right without thinking about it. So here we integrate this equation with separated variables. So here we put the sign of the integral this way, the sign integral this way, and let's throw in the boundaries of integration right away. We can do it. So for y, how do we integrate this expression and y? Well, initially, remember at time t0, remember all our observations that we made earlier. At this point, what was the initial time t equals 0? What was the initial value of y? It was d0. So this d0 goes over here, d0. And what is the upper boundary? Well, it is the current value, y. Also, get used to this. This is nothing complicated. You'll be doing this all the time. So grow up and figure out that that is a way to go. Now, let's go to the left side of this. What is going on over here? Which boundaries we apply over here and why? Well, remember, z stands for dx over dy, or the first derivative of x with respect to y. If you were more or less involved with mathematics in high school, then you usually dealt with the reciprocal of this dy over dx, but this is nothing really complicated. In some sense, again, very intuitively, your y-axis becomes the x-axis and the x-axis becomes the y-axis. This is it. This is nothing complicated. We already made all sorts of kinematic observations. So here at this point, what is the value of dx over dy? It is 0, exactly. So we integrate from 0 to what? To the current value of z. The current value of z, and this is it. So here also comes another point which will bubble up to the top of our discussions time and time again. Amongst all other, your ability to do grown-up mathematics, applying the theory of groups to the material and theoretical physics, and on and on and on, linear algebra, tensors, this and that, schmenzers, you will also need to be able to be minimally proficient with integration. Look at this. The integrals in theoretical physics are an integral and inseparable part of your business. You need to be at the level where you can integrate efficiently. You do not need to be the top integrator, but you need to be efficient with this, because if you cannot evaluate these integrals, you will not solve the problems, you will fail the exams, you will not be a happy camper. Now, this integral over here, we evaluated in the public setting, season 2, sorry, that was season 2, episode 53. Season 2, episode 53, that was in lieu of the problem S2M53. That is when we studied the mathematical equivalence. Remember, we solved one and the same problem in two different ways, the rotating pipe or the rotating rod with a small bead on it, and we deduced the law, the Lanchester square law, two armies fighting out under ideal conditions. All the integrals also are indexed in the integrals PDF, and the link to this integrals index all over the place. So find this episode, see how we evaluate this integral. Again, you've heard it here, season 2, episode 53. Find it on this channel. Use season guide, for example. In season guide, I link all the episodes. Click on the PDF and download it. I'll pop this video open in a separate tab, watch it, but this is basically, at this point, we take it as known. So the answer here is the following. The natural logarithm, again, absolute value. Pedantically, mathematicians will hound you to the end of days if you don't do this. So this is z plus square root of 1 plus z squared, absolute value, evaluated between 0 and z, and this guy we can write down right away. Let's do it this way. It will be the natural logarithm of absolute value of y over d0 raised to the power of rho. That much you should be able to swing on your own. Log y minus log d0 minus converts into ratio, rho in front, jumps into power, boom, you are done. Now let's look at this. At the lower boundary of integration, when z is equal to 0, 0, 0 plus anything is anything. Anything is what? Square root of 1 plus z squared. Z is 0, 0 squared is 0, 1 plus 0 is 1, square root of 1, 1, log of 1 is 0. Hallelujah, it's gone. So what remains of this guy? What remains of this guy is the following. Natural log of z plus square root of 1 plus z squared equal to log of y over d0. Again, here, throwing pedantic mathematics a little bit. When we have this equality in complex analysis with multi-valued functions, we have to be extremely careful, but this is real analysis, real mathematics, pun intended. So what do we have here? The function of logarithm log x, where x is real, is what? It is continuous on its domain, natural domain, and it is monotonically increasing. This is 1, this is 0, orthogonal, this and that. So if we have two values of the logarithm equal one another, then inevitably that means what? The argument must be exactly the same. So we have the right to basically omit the logs and write down the following. Z plus square root of 1 plus z squared is equal to y over d0 raised to the power of rho. And now from here you can proceed in different ways. If you are still wearing your high school skin on, you did not shed your high school skin, you will do here what I saw it many times. The way you will proceed over here is as follows. You will rewrite this expression as follows. 1 plus z squared is equal to, let's write this temporarily, let's write this as beta, so we don't have to write it. Beta minus z. Square both sides. Again, remember the square, the real square is again continuous, monotonically increasing and all that. So we have 1 plus z squared is equal to beta squared minus 2 beta z plus z squared. Here you will be happy to see that z squares cancel out. This guy, you have what? 2 beta z is equal to beta squared minus 1. And now you want to isolate z, so you divide both sides of the right-hand side of the equal sign by what? By 2 copies of beta. So from here, you will obtain what? That z is equal to 1/2 beta, because this kills 1 copy of beta here, and it will be minus 1/2 of beta, the reciprocal, beta raised to the negative power. This is a typical high school thinking, high school reasoning, and in some sense there is nothing wrong with that. But more grown-up mathematicians will do the following. From here, we know that the reciprocal of this quantity will be what? We'll multiply both sides by the conjugate minus z plus this. Squares will cancel out, 1 will remain, so you will write the following. Right away you will know that minus z plus 1 plus z squared will be beta minus 1. This will be the reciprocal. And now you have z plus square root of 1 plus z squared equal to beta. What do you do now? You add these two things. Exactly. When you add them, these guys cancel out, so you will have twice the square root is equal to beta plus beta minus 1. Here is the plus sign. Remember this, plus sign. Once you divide through, you will have the square root is equal to 1/2 beta plus 1/2 beta minus 1. But here we have 1 plus z squared. So here at this point, yes, when you square both sides, here will be 1. Twice the product of these two guys will be what? It will be plus 1/2. Plus 1/2. Here will be plus 1/2. But here you will have 1. When you move 1 over here, the plus 1 will become minus 1/2. And this will be what? This will be a perfect square. Again, you will collapse it back into a perfect square. So here the bottom line is that you will obtain exactly the same expression. So here we have our z, which is, remember, for our symbolic sugar it was dx over dy. It will be what? 1/2 of y divided by d0 raised to the power of rho minus, don't forget, minus 1/2 of y divided by d0, but to the power minus rho. You see, this is the expression that you are expected to generate on your own. This is the expression that you're expected to generate on your own. And now what do you have? Well, now you separated the variable for one more, but the final time. You keep dx over here, dy goes over here, and what are these integrals? Well, these are trivial, but we need to be careful because look at this. From the structure of this material that we're about to integrate follows what? We need to consider two cases where rho is not 1. Because this over here, remember, if rho is 1, we have a different integral. We have a natural log versus not. And when the second case, when rho is 1. So we will take on first the case where rho is not equal to 1 and integrate this expression. As I mentioned earlier, we separate the variables in this differential equation one more time. We multiply both sides of this equation by one copy of dy, and we obtain dx on the left. And here we can separate things right away. We will have, let me write it down this way suggestively, it will be 1/2. We'll leave the room of y over d0 raised to the power of rho dy minus 1/2, some room for something, y over d0 raised to the power minus rho dy as well. And we take first the case when the rho, the ratio, remember that rho is the ratio of velocity of the runner to the velocity of the chaser is not equal to 0. Technically, that means that our beloved friend Wile Coyote and the road runner are moving at different speeds, not at the same speed. We will consider the same speed case, rho equals 1 separately. So here what do? Well, we evidently integrate this bad puppy through. And again, you already know the boundaries of integration for y. It will be from d0 to y, from d0 to y. And what's going on with x? What are the boundaries of integration for x? Well, remember, we explained the reason why the origin is where it is. So from that point onward, when we launch the clock, that is our initial time. So at that time, the x coordinate of the Wile Coyote was what? Was 0. And at some point, it is x. So we integrate from 0 to x. Now, on the left-hand side here, we trivially have x, right? We'll have x right away. And here we will have also this, because remember, rho is not equal to 1. This integral is what? It will be 1 divided by 2 times d0 raised to the power of rho times y raised to the power of rho plus 1 divided by rho plus 1 evaluated between d0 and y minus will be what? Well, we'll put d0 on top, d0 raised to the power of rho divided by 2 times y minus rho plus 1 divided by, well, let's write it 1 minus rho evaluated also at between d0 and y. So here we will have evidently two terms. We figure that the two constant terms here can be combined into one. So we will have one constant term and two non-constant terms. This is our analytic expression for the shape of the trajectory, x and y tied together into one beautiful relationship. So what are the results? Well, let's do this. At the upper boundary for the first term over here, we will have our result. We will have 1 over 2 d0 raised to the power of rho times y raised to the power of 1 plus rho divided by 1 plus rho. And in order to make this expression a little bit more digestible, we can multiply the numerator of this ratio by d0 and divide by it. So we multiply here. So this will be plus 1 also. See, this rho plus 1, rho plus 1. So we can merge this, guys, into one. Wonderful. Minus, let's do the constant term at d0. So we have 1 over 2 d0 raised to the power of rho times what it will be. It will be d0 raised to the power of rho times d0. We'll write it suggestively like so, rho plus 1 divided by 1 plus rho minus, this is our second term, minus. Again, here we will have our, at the upper boundary of integration, we will have essentially the same term. We will write it like so, d0 raised to the power of rho divided by 2 times y raised to the power 1 minus rho divided by 1 minus rho. And here we'll do the same thing. We'll multiply this numerator by 1 copy of d0, divide over here, and once we move this into the denominator of the denominator, again, we'll be able to merge y over d0. Now here we have minus, remember, don't forget minus, so the second term becomes what? Becomes plus, correctly. So now we have d0 raised to the power of rho divided by 2 times, let's put it this way, it will be what? d0 divided by d0 raised to the power of rho times 1 minus rho. That maneuver is understood, right? This is d raised to the power of 1 minus rho because we replace y with d0. And what do we see? Well, let's work on the constant terms. Let's work on this term right here and this term right here first. Look at this. d0 raised to the power of rho, d0 raised to the power of rho cancel out. Same thing over here. One copy cancel out. And what do we have? Let's do this arithmetic over here on the side. So we will grab this term because this is with the plus sign, d0 over 2. So we have d0 over 2 times 1 over 1 minus rho minus d0 over 2 times 1 plus rho. So far so good, nothing complicated. This is middle school arithmetic. So we have d0 over rho times, look at this, so we have 1 plus rho minus 1 plus rho divided by 1 minus rho squared. Would you agree? 1 plus rho goes on the numerator of this ratio, minus 1 minus rho, so minus 1 plus rho, 2 copies of rho. This is not rho, this is 2, I apologize, 2. So 1 and minus 1 cancel out, 2 copies of rho, and these 2 cancel out. So what do we have in the end? In the end, we have this beautiful term. Look at this. d0 times rho divided by 1 minus rho squared. This is the contribution of this constant and this constant term, and we can erase this material. You understand how it came into existence. This is, again, nothing but middle school arithmetic. And now all we have to do is write down carefully. Look at this. We multiplied and divide this ratio in front of this expression by 1 copy of d0. So we have plus d0 divided by 2 times 1 plus rho times y divided by d0 raised to the power of 1 plus rho. That much we understand. This is not complicated. Now here, again, if you want me to spell it out, so let's spell it out like this. This expression will have the following shape: d0 raised to the power of rho divided by 2. Now look at this, one copy of y over here, one copy of y over here, y raised to the power of rho, and of course divided by 1 minus rho. So far so good. Now multiply this by d0 and multiply this by d0 here. Now this and this goes into here. You see, it goes into here with one copy, so it will be d0 with the power 1 minus rho. So that expression over here becomes this, minus d0 divided by 2 copies of 1 minus rho times, still the same thing, y over d0, but in the power of 1 minus rho. You see, this is it. So this is our expression for x. This is x. Let me put it into a box. This is x under condition, don't forget, this is under condition that rho is distinct from the positive unity. Again, this is as simple as possible, but not simpler, as much as I can muster. If you have any questions, use the comment section under this episode. And now, next, we will take on the case when rho, the ratio of the velocities of the runner and the chaser, is precisely 1. In this case, look at this. This is minus 1, this is 1, and the result will be quite evident. For the case when the ratio of the velocities of the runner and the chaser is precisely 1, which means the Wile E. Coyote runs at the same speed as the road runner, you do not need me. This is very straightforward. Here for the second term we have negative 1 power minus 1. Here we have positive power plus 1. So when we separate the variables one more time, dx is equal to this term times dy minus this term times dy. We integrate over the same boundaries from d0 to y, from d0 to y, from 0 to x. Here we have x again. And this integral is a baby integral, y squared over 2. When 2 and 2 collide in the denominator, they generate 4. But I wrote it down for you here so that you can follow the computations in a very transparent manner. Likewise, for this integral over here, we have the logarithm of the absolute value of y, d0 over 2 times the logarithm of y evaluated between the boundaries of d0 and y. And this is very straightforward. Here we have y squared at the upper boundary, y squared over 4 copies of d0 minus here d0 squared over d0. Only 1 copy of d survives in the numerator. Here is the same ratio again, y to d0, the basic property of logarithms. But it is slightly more convenient to rewrite this expression over here for the shape of the trajectory of the chaser C if we factor out 1 copy of d0 over 4 as shown over here. In this case, in the first term, we have d0 moving into the denominator, and we have a nice ratio of y to d0 squared minus 2 copies of logarithm of y over d0 minus 1. This is the shape of this time it's called the curve of pursuit. The curve of pursuit when the ratio rho is equal to 1. In the previous case, we had the curve of pursuit, an analytic expression that basically can be represented again as like this function of xy equal to 0 in general case. But in both cases, these curves are called a curve of pursuit. And now, since we solve this problem completely, we have the trajectory or the curve of pursuit of the chaser C in both cases when the ratio of the velocities is distinct from positive unity. And when it is exactly the positive unity, we can answer the second question of this problem, or the condition and the coordinate of the intercept. Now that we established the exact analytic shape of the curve of pursuit in both cases, when the velocities of the runner and the chaser are distinct from one, and when their ratios is precisely 1, we can answer the second question, the condition and the coordinate of the intercept. So the condition for the intercept will be obviously when the ratio in our designation is strictly less than 1, meaning that the velocity of the runner is less than the velocity of the chaser, and in this case, this curve of pursuit, the shape of the analytic shape of this curve of pursuit shown on top is applicable. This is how the integrals came out. It is a small miracle that these integrals are expressible as a finite combination of elementary functions, but lucky us. We know that in this case, what can happen? What is the basic condition for the event of intercept? Well, the runner runs only along a straight line. So if an intercept can happen, it means that the point C must coincide with the point R. And that means that the vertical displacement of the point C, if we write it down as xy over here like this, must be what? Not the displacement, but the coordinate must be 0 exactly. So here we put 0 into this expression. 0, 0, these two terms vanish. This is the only term that remains. And here we have our answer for the intercept coordinate. It is equal to the initial distance between the chaser and the runner, multiplied by this ratio, rho divided by 1 minus rho squared. But if we spell out rho, this is exactly what we have, the ratio of velocities divided by 1 minus square of this ratio of velocities. This is the coordinate of the intercept event. Now, when the ratio of the velocities of the runner and the chaser is precisely 1 or the identical one, then we can show that this can never happen, the intercept can never happen, because we compute the limit of our coordinate x when y tends to 0 from the right. And in this case, we take our second expression shown over here when y tends to 0. Look at this. This is a constant. Y raised to the second power, when it tends to 0, it vanishes. Here is a constant, but look at this, what happens over here. When y tends to 0 from above, from the right or from the top, let's say, remember the graph of logarithm, it goes this way. So when the argument here approaches 0 from this side, then the value goes to where? To minus 2, negative infinity. Negative infinity, minus times minus is plus, so the limit in this case of this expression will be positive infinity, which is to say that in this case, when the ratio of the velocities of the runner and the chaser is the same, both run at the same speed, then the intercept event, if you will happen at the point at infinity. And that means that in this case, again, I did not bother you with the graphs prior to preparing this episode. I experimented with all sorts of graphs. I recommend that you do that too. Here in US, I use the online this time tool. It's called Desmos. It allows you to graph precisely these types of expressions that look quite involved. But you will see that if you graph this particular function using Desmos, for example, or your favorite tool that allows you to graph it, then you will see that in this case, due to this result, the x-axis, our x-axis over which the runner runs, plays the role of what? It plays the role of the horizontal asymptote. And depending on the numbers that you dial in over here when you play with them, basically in this case, your curve of pursuit will look as follows. It will somehow bend this way. It will touch the y-axis. It will be tangent to the y-axis at this point, d0, but then it will fairly quickly get to the x-axis, but then it will stay arbitrarily close to it and never touch it. That's the notion of the horizontal asymptote, and this proves that the condition for the intercept is right here. The velocity of the runner has to be strictly less than the velocity of the chaser, or in positive terms, chaser has to run faster than the runner. This is the coordinate of the intercept. In a few minutes, we will compute the time that it takes for the intercept event to happen, if it happens. But right now, let us deep dive a little bit more into the kinematics of Wile, Coyote, and Roadrunner, as I advertised in the title of this episode. And we will, and in order to do that, we'll construct the function that will capture the distance, the linear distance between these points as the function of the locally available material. And regardless of how fancy the curve of pursuit in this case is, we can always connect the point C, the chaser, and the point R, and look at the linear distance between of them, CR. And this is what we will do in this segment. Again, you have all the material that you need in order to construct these relations by yourself. This is just, I'll give you this for a reference with the correct response, if you will. So the difference CR is given by the Pythagorean theorem from the right triangle CPR, where P is the orthogonal projection of the point C onto the x-axis. We know that the distance CP is the y-coordinate. Once we factor it out, we move it into the denominator of the second term, and we already showed, remember earlier, I told you that we will reuse this relation when we constructed dx to dy when we were projecting the velocity vector of the chaser. We came to this relation. Don't forget the minus sign, but because we square both sides, the minus sign disappears. So this is the expression for the distance between the points C and R prior to the intercept event at all times in terms of the locally available material, variables x and y, or the coordinate of the point C, the chaser. And once we recall the other relation that we had when we unwound separated the variables for our ordinary differential equation and prepared it for integration. This is the relation that we had, remember. We obtained it in two ways, the high school way and slightly more mature way. But now if we take this and put it back into the square, once we spell it out, here we will have minus 1/2. But then there is 1. So 1 minus 1/2 plus 1/2. This collapses into a perfect square, square root of the perfect square. In general, it will be plus minus, but for the distance, we'll take the plus. So once we unwind these relations, then we have this relation. Now, one copy of y sits in front, don't forget. So we bring it in, and this is the expression 1/2 y raised to the power of rho plus 1 over d0 raised to the power rho plus d0 in the numerator now raised to the power of rho, and then y raised to the power of rho minus 1. Don't forget. So this is the equation for the distance between the points, between the chaser and the runner. And now you can analyze it and go to town in any which way. Here I wrote down for you 3 cases. In the first case, when the ratio of the velocities is strictly greater than 1, what does that mean? That means that the velocity of the runner is way more, let's say, than the velocity of the chaser. This is the usual case in the American cartoon. The Wile E. Coyote usually never can catch up with the runner, so the road runner runs faster than the Wile E. Coyote. In this case, look at this. This term disappears, vanishes, it becomes 0. But here we have still rho is greater than 1, so the power into which the argument y is raised is strictly positive. So when it tends to 0, this tends to 0, 1 over 0 in the limit positive infinity. That means that when the velocity of the runner is higher than the velocity of the chaser, what happens to the distance in the limit? The distance grows without bound, and the chaser has no hope of catching up to the runner whatsoever. When the ratio of the velocities is precisely or the identical one, then we have the following situation over here. Look, 1 is gone, it collapses into 2. 1 minus 1, 0, that becomes 0. This is quite interesting. So this term in the limit vanishes, but this constant survives. So in the limit, when y tends to 0, so basically the chaser or the pursuer gets closer and closer to the x-axis, then this distance stabilizes asymptotically at 1/2 the initial distance, d0 divided by 2, d0 divided by 2. And in the final case, when rho is less than 1, this is again very fundamental, rudimentary real analysis. The distance CR in the limit y tending to 0 is 0. That can be seen quite quickly. Over here, this term again disappears anyway, vanishes. And then for the term in the denominator, the second term in the denominator, look at this, rho is less than 1. Let's say 0.7 minus 1 minus 0.3. So we represent it as minus epsilon, but epsilon is taken to be what? Strictly positive real number, which it will be. And in this case, our 1 over y raised to the power negative epsilon becomes y raised to the power epsilon. This is a non-zero real number. Y tends to 0 is 0. And that means that in this case, as we have shown, the chaser catches up to the runner, the intercept event does take place, and we computed all the parameters. We computed the shape, the analytic shape of this particular curve of pursuit. It is interesting to graph it again. You should do it on your own without my help. And we also computed the coordinates of the intercept point when the point C catches up to the point R. This is the intercept event. CR, we call this distance xi. We know what the distance is. So this shows you the rudimentary kinematics of the Wile, Coyote, and the Roadrunner. As I promised in the title of this episode, you can analyze it probably further, but now we have one more question to answer, and that is compute the intercept time. And before we compute the intercept time of the point R by the point C, let us play a little game, because again, invariably, this material on the one hand seems or comes across when explained to a person, to a student who did not make these observations, as very simple. On the other hand, how come some students cannot make these observations? Let us take a very literally middle school case when there is a pure linear pursuit. The point C, the chaser runs after the point R in a straight line, both cases, in all the cases, in the first case, in the second case, and in the third case. We will designate the linear distance between the points C and R with the lowercase l, L, and L. In the first case, the velocity of the chaser is the same as the velocity of the reader. So the game is this. I will ask you a question and you tell me what the answer is. So the question is, in the first case, when the velocity of the chaser is exactly the same as the velocity of the runner, what happens to the linear distance between these 2 points? So these 2 points run at the same rate along the straight line, let's say. What happens to the distance? Well, the distance does not change. What can you say about the first time derivative of dl over dt? This derivative is an identical 0. The distance, this quantity does not change. Let's take the second case. The velocity of the chaser is smaller than the velocity of the runner. So in other words, these 2 points run in such a way that over time the runner gets away further and further and further away from the chaser. In this case, what happens to the linear distance between the points C and R? That distance grows. So the question is, what can you tell me about the first derivative of dl over dt? The answer is correct. This time the derivative will be strictly greater than 0, because again, when the magnitude grows, the rate of its growth is strictly positive. The third and the final case, purely linear pursuit, the velocity of the chaser is this time strictly larger than the velocity of the runner. What happens to the distance when these 2 points run, but the chaser comes up faster and faster and faster to the runner? What happens to the behavior? How does the linear distance behave? Well, this distance shrinks. What can you tell me about the first derivative of dl over dt in this case? Well, in this case, evidently, it's less than 0. It's negative because the magnitude decreases and the rate of its change is negative. Again, basic, rudimentary, fundamental. In some sense, I'm exaggerating, but only slightly for demonstration purposes. This is purely middle school material. Now, in this case, what is the relative velocity of one point with respect to another when the velocities are the same? It's 0. In this case, when the velocity of the runner is larger than the velocity of the chaser, what happens to the, let's say, separation velocity? What is the separation velocity? Well, from the larger velocity, Vr, we subtract the velocity of the chaser, because in the limiting case, let's say the chaser right now all of a sudden out of breath, stands still, but the runner has enough lungs to keep cranking and runs away. At what rate do these 2 points separate? At the rate Vr. But when the chaser is running, and has the legs to run, it will be the velocity of separation of these points. Remember, the distance between them grows, will be given by this difference. This case, when the velocity of the chaser is larger, strictly larger than the velocity of the runner, what happens to the distance? Well, it will be the convergence. Convergence velocity will be what? In this case, it will be the other way around. Still, from the larger quantity, velocity of the chaser, we subtract the velocity of the runner, because in this case, let's say the runner has no more lung, has no more legs, stands still. At what rate will the chaser converge onto the runner? At its own rate, velocity vc, at velocity vc. That's it. These are the basic observations, and this is all that is needed in order to compute the separation time. And now, once that is understood, let us carry out the actual computations together. For the actual computation of the intercept time, let us think together. When and if the intercept event happens, so when the point C eventually caught up to the point R, we know that the point R runs along our real axis X, and the point C can only intercept it there, so both points are now sitting on the X-axis. How long did it take for the point C to catch up to it, starting from this point? And remember that this distance right here is what? This distance is d0. What is the first condition that comes to mind, which can be converted into actionable physics over here, the condition of the intercept event? Well, it should be evident right away that the first condition is the following. The horizontal displacement of both points must be the same. In other words, the horizontal displacement of the point C, which traveled this far, the intercept point, and the horizontal displacement of the point R. It also must be exactly the same. It all happened at the intercept coordinate xi, which we already computed. We know what the deal is with the intercept. So we write it as follows. The horizontal displacement delta x of the chaser must be the same as the horizontal displacement of the runner. This is an evident condition, doesn't really take much to figure out. You do not have to be an Einstein to see that. This is the straightforward, street smart, so to speak, condition, and we already can write down the right hand side of it. What is the horizontal displacement of the point R? Well, starting from here, it ran. Remember, we launched the clock at that point. How much distance did it cover? This is our proverbial distance OR in this case. And what is this? The velocity of the runner times what? Times tau. And tau this time will be what? Exactly the intercept time. Tau, now remember, tau is the intercept time. Wonderful. What can we say about the horizontal displacement of the point C, of the chaser? Well, this is also straightforward. Its velocity vector at any point varies in some intricate but interesting fashion at any time. It remains tangent. So let's say our point C is right here. Its velocity is tangent, it points this way, and what is this? If we continue, this will be our point. This will be the runner. We know the drill, this angle alpha. So what component or what portion of the overall velocity of the chaser C, let's say, moves it, intuitively speaking, in the horizontal direction for the horizontal displacement? Which point? Well, which component? This is the X projection of this velocity. So let's say the velocity, dx over dt, this is how we started reasoning at the beginning of this episode, is equal to velocity of the chaser times the cosine of angle alpha. And this angle alpha, now we write it down as some perhaps intricate, involved, possibly quite horrible function of time. We do not know what it is, but that is what it is. Now we multiply, we separate the variables over here in this quite elegant differential equation dt, and we integrate both sides. From where? From 0 to the intercept point, from 0 to the intercept point. xi, this is our xi, and here we integrate from, because we integrate over time, from 0 to the intercept time. Make sense? That is very straightforward. Now this will be xi minus 0, by definition, this is our delta x, the horizontal displacement of the chaser, delta xc. And what is this? Well, remember that this portion is constant, so we can rewrite this as follows. It will be the velocity of the chaser, vc, times the integral I, possibly quite horrible, but this integral will look as follows: from 0 to tau cosine of the angle alpha, which is a function of time, dt. We will not be computing it, but we will designate it like so. This times this is our displacement. But this horizontal displacement of the chaser, remember, they both of these points stepped away from the y-axis along the horizontal direction by the same amount. So now this must be equal to this, you see, velocity of the runner times tau. So this is our relation number one. Don't forget, don't be confused. This is angle alpha. We know that the velocity of the chaser always points towards the runner r. So these observations about angles we already made, but now we have one relation. What is the second? Condition that we need? Because we did not compute the angle alpha as a function of time. We do not know what this integral is right now as we speak, but we can cook up a second condition for the intercept. What is the second condition? Well, the second condition is also, in some sense, comes from the land of street smarts. We do not really need to be, Einsteins, Newtons, or Leonard Euler's to figure this out. Initially, the distance between the point C, this is the point C at the initial state, and the point R at the initial state was what? Was d0. But when the intercept event did take place, what is this distance? This distance is 0. Exactly. So the distance, the straight line distance between these 2 points shrunk to 0, starting from d0. Now, this is where the experiment that we just conducted a few seconds ago will come in helpful. Now, despite the fact that the chaser C moves over some fancy curve, even though we have the analytic expression for that curve, the curve of pursuit in this particular case, no one can prevent us from connecting the 2 points prior to the intercept event with a straight line. There always exists, prior to the intercept event, this distance right here, this distance, L, is always there. So what can we say about this distance? If I write down this minus dl over dt, we just conducted this experiment together a few seconds ago. What is the rate at which the distance between these 2 points shrinks under favorable condition, under finally our favorite friend Wile Coyote may catch up to the road runner? If that distance shrinks, what is the expression for it? Well, from the higher velocity of the chaser, we subtract. But this time, remember, in the first case, when we deduced this relation, we projected the vector of the velocity of the chaser onto the x-axis. But now for the straight line case, when we connect the runner and the chaser with a straight line, we always have this straight line over here running this way. And now we project here, let me show you with red perhaps. Let's say this is the velocity of the runner. So now we project it onto this straight line. Orthogonal projection, but according to Euclid's Elements, book number 1, remember Isaac Newton at the age of 23 knew the elements by Euclid back and forth like the back of his hand. So here these angles are vertical, so it's the same angle. So now we project not the velocity of the chaser, but the velocity of the runner onto that straight line direction. You see, this is the maneuver that you were expected to carry out on your own. So this will be what? Minus the velocity of the runner times the cosine of the angle alpha, which is some intricate and possibly horrible function of time. You see, this is what's going on. Again, elementary differential equation. Let us separate the variables. Minus dl is equal to velocity of the chaser times dt minus velocity of the runner times cosine of t dt. What do you do next? What's your next step? Well, integrate. What do we integrate this from? Well, initial distance was d0. What's the final distance? when these 2 points converge and the intercept event did take place? 0. The distance is 0, so the upper boundary 0. Here, all the integrations for time go from 0 to intercept time, from 0 to intercept time, tau. So what is this? This is minus 0 minus d0 on the left-hand side. This integral is as babish as they come. So velocity of the chaser times the intercept time tau minus vr times, once we move, because velocity of the runner is constant, we move it from the integral. What do we have? We have our favorite character. We have I again. And what is this? 0 minus this. So d0 is equal to velocity of the chaser times the intercept time minus velocity of the runner times. Let's be brave and write down the expression for this potentially horrible integral. Will be what? Velocity of the runner, so square, divided by velocity of the chaser times the intercept time tau. So tau here, let's factor it out together. So we have, and bring this into the same denominator. So velocity of the chaser squared minus velocity of the runner squared divided by the velocity of the chaser times tau, and all this beautiful mess is equal to d0. From here it follows what? Let's write down the expression for the intercept time tau. We now know what it is. It's actually quite beautiful and quite elegant. So it will be d0 times velocity of the chaser in the numerator divided by the difference in squares, velocity square of the chaser minus the velocity square of the runner. Make sure you get this information right. Why? Because time in this case we take to be a strictly, well, in this case, even positive real number. It has to be positive real number. Look at this. You see? And what happens in this case? Well, we have a difference of squares, but by magnitude, we know, remember, we deduced in the previous case, the velocity of the chaser must be larger than the velocity of the runner. Only then intercept event happens, and only under these conditions, our formulas here make sense. So this will always be what? Not only not 0, but this will be strictly positive quantity. Positive quantity, positive quantity. So this time, the intercept time is a positive quantity. Now, look at the magic of how physics and mathematics work together. Here is another little thing I would like you to pay attention to. Let's say, take a good note of this reasoning, but we can write down, look at this, from this relation, once we know the intercept time, we actually know the value of this potentially scary and horrible integral. And what is the value of this integral? Well, look at this. I is equal to intercept time, which we have over here, times the velocity of the runner divided by the velocity of the chaser. But if we see the velocity of the chaser in the numerator, denominator cancel out. So for the integral I, we have d0, pretty much the structure is the same, but here will be what? The velocity of whom? The runner or the chaser? The runner. So let's write down this expression right here. We can already do it. If you want to, I will move this expression over here. We have v r times tau equals vc times I. This is equation. So here I is equal to velocity of the runner divided by the velocity of the chaser times tau over here. You see this? Now velocity of the chaser in the denominator and numerator cancel out. So here we have this wonderful result. It will be d0 velocity of the runner divided by square of the chaser minus square of the runner. Obviously the velocities I mean by that. And look at this. If we undertake the job of figuring out all these things, computing, for example, how specifically angle varies over time, this will be probably an involved function, and the integral will be probably scary and horrible. But regardless of that, this is how this is the magic of mathematics and physics. We may not know or may not be able at a moment to evaluate this definite Riemann integral, but we know its value. So see, catch this delicate situation over here. The line of reasoning that starts with the integral and winds up with the answer may not be known to us. It may be obscured, but we know what the answer is. This is the answer right here. This is the guy. So this is the magic of mathematics. This is how mathematics and physics work together. And now that you understood and how the intercept time can be computed, you see this formula right here, we will move on to a new challenge next. Wonderful. Our next challenge will be challenging computer science. It will be the problem S3CS10, and it's formulated in a very straightforward manner. Construct a practically useful big O of one-time complexity algorithm, and of course, and as usual, we would like to hear your story. In other words, tell us your story, how such an algorithm can be designed. Now, this is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my practically useful big O of one-time complexity algorithm.